Good afternoon, everyone. Well, it's afternoon for me, maybe not for you. Um, Time to do a little bit of probability and statistics. For those of you who are in probability and statistics, this will be most likely the first time that you see me doing things in this particular environment. I'm going to use some uh, iPad screen mirroring technology to write stuff down and interact with you, hopefully more effectively in that way. And I will kind of flip back and forth between, my iPad screen and the actual notes themselves. And I will say to the problem and stats people, if you want a little bit of a deeper dive into the exponential and gamma distributions, there are a couple of videos I've posted to the playlist for the theory of probability class. You'll be able to see them there for Monday, the 23rd of March's lectures, where I talk specifically about the connection to the Poisson with the exponential, and then how the gamma distribution is just a natural extension of the exponential. Okay, that's unfortunately something that gets glossed over quite a bit in courses like these, but I refuse to do that. I want you to be fully cognizant of all that is happening. Okay, so let's review for just a couple of seconds here, and then we'll jump right in. So remember, we talked about the exponential distribution with parameter lambda, and I said that it is no accident that that lambda is used, because that lambda is the same as the lambda that is in the the Poisson distribution. Okay, this is the density right here. This is the density. Here's a couple of graphs for various values of lambda. Okay, and this is the CDF. Okay, right here, this is the CDF. And again, over in those videos that I said you could go check out at your convenience if you wanted to, for the theory of probability people, we actually derive this and actually come up with the density function as well. It's pretty easy once you have the density to get the moment generating function, and it's given by this. So basically what's going on is the exponential distribution with parameter lambda, all it's doing is it's tracking the amount of time in a Poisson process until the first observation. Okay, so again, if you expected to see lambda equal to 2 observations in a 1 hour period of time, okay, if you expected to see 2 observations in a 1 hour period of time, then how long would you expect to have to wait to see the first observation? Well, 1/2 hours, or a half hour. So you kind of even see that explicitly right here in the formula for the expected value of x. Okay, and then I explained, we did these couple of problems as the exponential distribution has the so-called memoryless property. In those videos, you can also see me show why this happens to be true. We did those examples over there, but then we stumbled upon the gamma distribution, and that is built on the back of this thing called the gamma function. Okay, the gamma function is given by this integral. Okay, and this is used in something, and I said that it's an extension of the factorial function. So you could do things like gamma of pi, and that makes sense. But also gamma of various integers, like gamma of 5, for instance, is just 4 factorial. So the gamma function is a natural extension of the factorial function to other things that aren't integers. Okay. And the gamma distribution is given by this. And in those videos over there, I actually show why this is a density. And I get the moment generating function from which everything else follows. Okay. And essentially what I show over there is that the gamma distribution is basically just like the exponential, except that you are waiting not just for the first observation, but for the alpha observation. So like if alpha is 5, you're waiting for like the 5th observation, and you're recording the amount of time that that took to get to the 5th observation. So the connection I want you to have in your mind is that the gamma is to the exponential as the negative binomial was to the geometric. Okay, if you understand those words, that's awesome. Okay, that's an awesome thing that that, you know, I could say a sentence like that and you understand what it means. Okay, the negative binomial is to the geometric. Remember, the negative binomial was the amount of trials until the, you know, until the rth success. The geometric was the number of trials till the first success. So the negative binomial is to the geometric as the gamma is to the exponential. Okay, so the gamma is the amount of time that transpires in a Poisson process till I observe alpha occurrences, whereas the exponential was just waiting for the first occurrence. How much time went by until the first occurrence? Okay, so that's how you ought to think about the gamma and the exponential. Okay, in those videos, those extra videos I did for the theory of probability people, I actually derive this moment generating function, and everything else follows from that. Okay, but the relationship between this and the Poisson is that beta is equal to 1 over lambda in the Poisson process. Okay, so it's not surprising that the expectation is just alpha times beta, which beta is 1 over lambda, so it's alpha times 1 over lambda, right? And 1 over lambda was the expectation of x back here. And 1 over lambda is beta, so that variance right there is beta squared, and so you see that the variance is alpha times as large, alpha times beta squared. Okay, I'm going to skip this stuff about the incomplete gamma function. That gets a little wild and crazy, so I'm not going to do that right now. It's interesting, but it's not really necessary for us. Okay, so here's an example. Suppose that when a transistor of a certain type is subjected to an accelerated life test, the lifetime x in weeks has a gamma distribution with mean 24 weeks and the standard deviation 12 weeks. So x, okay, so x, right, the lifetime x in weeks is distributed as the gamma distribution with mean 24 weeks and standard deviation 12 weeks. So mean 24 weeks. Okay, mean 24 weeks. Okay, I'm writing this down so that we can use it in just a minute. Mean 24 weeks and variance. Okay, so the variance of x is equal to 12 squared. Standard deviation is 12. So that would be the square root of the variance. So the variance would be 12 squared. Okay, 12 squared. All right. So what does that mean? Okay. So first of all, you know what I'm going to do. So what is the probability that a transistor will last at most 24 weeks? Okay. So the probability that it will last at most 24 weeks. Okay. And is the median of the lifetime distribution less than 24? Okay, and so a follow-up question to that is the median lifetime distribution less than 24? Okay. So that's a couple of questions. And so what I'm going to do is I'm going to share my iPad screen. We're going to go over here and do some work, all right? So here we go. Okay, so screen mirroring. I've copied down the stuff that I just said. So X has the gamma distribution, okay? And usually when you say that, you want to express what alpha and beta are, okay? Now, one thing that we'll keep in mind, this thing said that the expected value of X was equal to 24. And you know that the expected value is just alpha beta, okay? So whatever alpha and beta are, I'm trying to figure out what those are, that the product has to equal 24. Okay, and what about this? So so this was equal to alpha beta squared. Alpha beta squared. Okay, so we know that alpha beta is equal to 24, and that alpha beta squared is equal to 12 squared. Okay, the standard deviation was 12, so the variance is 12 squared. Okay, so how in the world am I going to figure out what like alpha and beta are? Okay, so what's alpha? What's alpha? What's alpha and what's beta? Okay. Well, okay. So that's like the first thing we're going to need to figure out if we're going to be able to compute any of this. The other questions were saying, what is the probability that we're at most 24? That this thing is at most 24, and what's the probability? Or and is the question was, is the median smaller than 24? Okay, so that was the other question we wanted to get at. But right now we're interested, we have to first figure out what alpha and beta are. I know that alpha beta is equal to 24, and that alpha beta squared is equal to 12 squared. So let's sort that out, right? So alpha beta is equal to 24, and alpha beta squared is equal to 12 squared, okay, is equal to 12 squared, which, by the way, okay, so that's like 12 times 2 times 6, for instance, yeah, because that's 12 times 12 after all, okay, which is equal to 24 times 6. You might say to yourself, why is Hammett doing this? Well, watch this. Alpha beta squared is equal to 24 times 6. Alpha beta is equal to 24. So watch this. Do you see that beta is equal to alpha beta squared over alpha beta? Yeah, I mean, after all, the alphas would cancel, and so would one of the betas, and you would end up with beta. And so I can just straight plug these things in. This is like 24 times 6 over 24. And so this would be 6. And we have beta. And if beta is 6, okay, and we know that 24 is equal to alpha beta, which, by the way, we just figured out what beta was, so that's 6 alpha, okay? So 6 alpha is equal to 24. So what's alpha? Well, it's 4. So alpha is 4 and beta is 6. Alpha is 4 and beta is 6, yeah? So that's great. I think we have everything that we need here. So let's see. X, right? So X was our gamma. X was distributed as the gamma with alpha equal to 4. Okay, so it's kind of like waiting for the 4th observation in a Poisson process. And beta was equal to 6. And in this case, it's kind of strange because, you know, remember beta, if we're in a Poisson process, beta is equal to 1 over lambda, okay? So that means that lambda is like 1/6. So, I mean, it's sort of bizarre that we would be, you know, expecting to have 1/6 of an observation in our interval window here. Okay, but that's all right. That's a little bit strange. So I wanted the probability that X is at most 24, okay, if X is the gamma distribution, okay? So yeah, that's interesting. We can use Excel to like pull this off here. So that's what I want to do now is I'm going to open up Excel so we can go ahead and go in there. So let's do that. Here's Excel right here, right here. Okay. I want the probability that X is at most 24, where X is a gamma distribution with parameters alpha equal to 4 and beta equal to 6, which we just discovered. So right, if you go equals, again, you can be a complete idiot and still use the gamma. Okay, equals gamma. Ooh, there it is. Gamma distribution. Gamma distribution. Oops. What's going on here? What? Gamma distribution, yeah. X. Okay, so what's our X? X is like 24. Okay, what's alpha? Well, alpha was 4. Okay, what is beta? Beta was 6. Cumulative, well, yes. Okay, yes, it is cumulative. Okay, so the probability that X is less than or equal to 24 ends up being 0.56, 0.567. Okay, that's funny. 0.567. 0.567. Okay, so let's go back over here into my iPad, and I already wrote that down. Okay, here we go. Okay, so we get 0.567. Now the other question was, is the median smaller than 24? So is the median, is mu twiddle, the median, smaller than 24? Well, is it? The median is the 50th percentile. How much data have we accumulated once we're up to 24? Well, 56.7% of the data. That's too much, right? So the median indeed would have to be less than 24. Yes. And that's since the probability that X is less than or equal to 24 is bigger than 50%, right? It's bigger than 50%. So yes, the median is less than 24. Okay, so interesting. Okay, interesting. So so we've answered those questions. Let's go back in here and get a little bit more clarity on some things. So here we go. Okay, is the median of the lifetime distribution less than 24? Yes. Okay, so we have that for sure. Okay, so moving on. The chi-squared distribution, I'm going to move this a little bit. Chi-squared distribution is interesting. What it is, and it actually comes up, it'll come up later when we want to deal with some specific statistical parameters. Okay, the chi-squared distribution, turns out sometimes when we collect data, you know, we will end up having to use the chi-squared distribution. It utilizes the gamma distribution, but it's a special case. It's a special case of the gamma distribution where alpha is equal to r over 2, okay, and beta is equal to 2. Then you might say, man, what in the world what's up with that? What are we doing? Okay, well, and by the way, this right here is exactly what you get from the gamma distribution. This density right here is exactly what you get if you plug in alpha equal to r over 2 and beta equal to 2. That is what you get. Okay, and the one nice thing is you no longer have to refer to 2 parameters. Okay, you just have to refer to 1, namely r, and you call r the degrees of freedom. It'll become clearer later on what that even means. But just know that the chi-squared distribution for now is naturally gotten at from the gamma distribution if you take alpha to be r over 2 and beta to be 2. And you no longer need the 2 parameters, only the 1, namely r, the degrees of freedom. All right, so there's a couple of things we could write down that are just direct extensions of the gamma. Okay, namely, the mean is r. Remember that was alpha times beta. Well, alpha is r over 2 and beta is 2, so you get r. And sigma squared, that's the variance. Sigma squared was alpha beta squared, right? Was alpha times beta squared. Alpha was r over 2, beta was 2. So alpha over 2 times 2 squared is 4 times r over 2, and you get 2r. Okay, so there it is right there. And this right here is exactly what you get if you put beta equal to 2 and alpha equal to r over 2. Okay, so there it is. There's the moment generating function. And the notation is this is the Greek letter chi. It's not an x. Chi squared, the chi-squared distribution, and you have to give the degrees of freedom r in here. Okay, but just note it comes directly from the gamma. Okay, the gamma is the one here that is really where this all comes from. And something important here is like the tail. The tail of the chi-squared distribution is really important. When you get into hypothesis testing and statistics, the tail of the chi-squared distribution becomes very, very important. That just means that you want to measure the probability that x, which is the chi-squared random variable, is greater than or equal to something. Okay, and these somethings are actually given a name. So it's chi-squared, and you put a little sub p right here of r. This is a special number. It's the number such that the probability x is beyond it is just equal to p. Okay, so if the probability beyond this is p, the probability in front of it is 1 minus p. So this is at the 100 times 1 minus p percentile of the chi-squared distribution with r degrees of freedom. So this little formula right here is important. The probability that x is equal to or greater than this thing, the way that this is defined, okay, this little chi-squared sub p thing, the way that this is defined is that the probability that x is equal to or greater than that is equal to p, okay? Okay, we'll explain that in a little bit more detail here in just a second, okay? Now, here's an example that we'll do here in a second on the whiteboard here and on my iPad. But suppose that x is distributed as chi-squared 17, okay? So x distributed as chi-squared of 17, okay? Find these probabilities, okay? Find the probability that 6.408 is less than x, is less than 27.59, okay? Determine, so they want that probability. They want you to determine this funny little number, chi-squared sub 0.95 of 17, okay? And they want you to determine the chi-squared sub 0.025 of 17, or 17 degrees of freedom, okay? So those are the two things that we're going to do here on the whiteboard, okay? So first of all, I'm going to explain this a little bit more, and we'll go through this little problem right here. So let's go do that. Okay, here we go. There we are. Okay, so first of all, okay, so before we do these problems, I want to go back and explain this a little bit more. So what is this mysterious thing right here? Okay, well, the chi-squared distributions are a little bit strange. They look kind of like this. Okay, they look kind of like this. So first of all, the gamma distribution itself was only, right, remember the chi-squared comes from, it's a special case of the gamma. The gamma distributions only had stuff going on after 0. The chi-squared distributions look kind of like this, okay? They kind of go like that, okay? And what's the deal? So if x, so I'm assuming that like x has the chi-squared distribution with r degrees of freedom, okay? Then this little number that we're talking about, namely chi-squared, and you put a little sub p right here of r with r degrees of freedom, what it's saying is this area in the tail of this thing, from this point onward, what is that? Well, that's p. And if that's true, then what about the area? What about the area in this part right here? how much area would there be right here? Well, that would be 1 minus p. Okay, so that's why this number sits at the 1 minus pth, or 100 times 1 minus pth percentile. If you think about that for a second. Okay, so that's what this thing has. These chi-squared sub PR things, they talk about a number after which p, p is the percentage of data underneath the distribution curve. Okay, so with that in mind, let's go back over to here and do these couple of problems. Okay, so I want the probability that x is between 6.408 and 27.59. Okay, let's see that on the next page here. So again, what's x? X is distributed as chi-squared with 17 degrees of freedom. I want the probability that 6.4, was it 6.408? Yes, 6.408 is less than x, is less than, what was the other one? 27.59. Okay, 27.59. Okay, well, you know that that's going to be the cumulative distribution function for this thing, okay, which no doubt Excel will give us access to. It's the cumulative distribution function at 27.59 minus the cumulative distribution function at 6.408. Okay, which is equal to, well, I don't know. Let's check it out. Okay, let's go over to Excel and take a peek. Okay, so this is equal to, what do you think we're gonna type here? Chi-squared. Now you might be tempted to type an x, but they're not gonna know what you're talking about, all right? So what you do is you CH, and then it starts to say, ooh, chi-squared distribution. And actually notice that you're starting to see things like there's an RT right there, that's like right tail. So it turns out that, you know, things like that are going to start to become important to us here pretty soon. But I'll explain that in a minute. So the chi-squared distribution, okay, chi-squared distribution. Oh man, what is happening? Come on, man.